Distinguished colleagues, the time has started for the next session. We're starting the second session of our conference. This particular session will be dedicated to aerial and UAV survey and applications. And I will start this session, although I'm also a moderator, but I will make the first presentation here. And I will speak about VisionMap and the aerial sensor A3. I'm the scientific director of VisionMap. VisionMap was organized in 2004. We're 12 years this year already. For a number of years ago, it was sold off to two large industrial holdings in Israel, and a few months ago it was reorganized. One of these holdings, it is a famous defense company, Rafael. And now we are the so-called business unit of Rafael. In terms of our position on the market, nothing has changed. Still, we have two markets that we cover: defense and civil market, where we develop and promote our products on both of these markets. And this year we have made a lot of new design projects, mostly on software development, because A3 camera, it was 1 or 2 years ago, one has matured enough to become a very robust product, and we expect to update its functionality. But the way it is now, it has already reached its peak, which would require a totally new technological overhaul later on, but it's unlikely that we'll introduce a new sensor in the next year. But in a couple of years we are going to come up with something totally new. So that's why all these years were dedicated to mostly the software updates, the famous software at light speed, and through technical cooperation with our partners. Most of the companies come from Israel who supply additional functionality to the sensor, and I will show you what they are all about. Let us start with our company first. If you don't mind, I will move the thing here so that I could see what is on the screen. So it's a bit of a show and tell here. The main idea of A3 camera is to combine high land-based resolution, long focal lenses with large land coverage. Regular technology cannot achieve this because long focal lenses usually have very small angle of view and the coverage will be small. As a result, this way, in our case, we decide to resolve it by having two rotating lenses which are rotating against the line of the flight. This way we ensure 110 angle of view with very high land coverage, because the lenses have 300 millimeter focal length. The system looks like this. This is the camera itself, light speed. This is the software, automatic software that covers most of the photogrammetric functions. I will speak about it later. And also functionally, we provide the ground-based processing system, which can be supplied either by us. It is a turnkey configured solution, or the user can buy it on site. These systems are good because they have a warranty period of 3 to 5 years. They're already quite inexpensive, I'd say now, and they have high performance. The software license can be scaled up to based on the number of cores in the system. So your performance will largely depend on the capacity of your system, and as long as the whole system works on parallel, we have a parallel processing. And then if you have some large global projects which you would like to finish faster, then you can buy a license for a bigger number of cores. Or if you have, say, 10 projects per year, 10,000, tens of thousands of square kilometers, then you don't need such processing system. You can live with a lower performance system. This is what the parameters of the system looks like, and as I told you, 300 is the focal length of the lens, the changing angle view, the maximum size is 110 degrees. Pixel size, we still use CCD here. We haven't moved to CMOS yet. We are studying this opportunity. So far it's not clear for us, so we are using a standard CCD with 7.4 micron resolution. Another interesting thing, usually companies are proud of the size of the image that they acquire. They say that we have, for instance, 200 million megapixels, 200 megapixels, 300 megapixels. The maximum size is 800 megapixels per one frame, which, if you're flying with a maximum field of view, then you'll have a large image like this. The system allows us to acquire data in regular colored RGB and RGB near infrared. These are two different modes. When we work in RGB mode, near, the performance of when we speak about performance, it's aerial photography performance. How many square kilometers can be covered per hour with this ground resolution. So in this mode, the productivity would be 2 times less than the productivity in RGB mode, but still it will be higher than any other systems available on the market can offer. The system, as you understand, must have a compensation or image shifting capability. And in our case, we have, first of all, the movement of the plane, forward motion compensation that we need to have. Then there is a movement of the lenses, and this movement also needs to be compensated, and some plane vibrations as well. We don't have gyrostabilizing thing. Well, we do have some stabilizer, but we have a totally different form of resolving this. And this system, which is compensating the image shift, is responsible for all of these parameters, like plane movement, rotation of the camera, and plane vibration. The system is lightweight, small, just 42 kilometers weight, and it is supplied in a single module made up of 3 modules. The maximum weight of a single module is 25 kilos, and one single person can mount it on a standard plane. What are the main specs of the system? Very high productivity or performance, the highest productivity at the moment among similar photogrammetric systems in the world. Depending on the altitude and the speed of the plane, we can have a maximum productivity of up to 11,000 square kilometers per hour. So you're flying 1 hour, and in 1 hour you get 11,000 square kilometers of data. Good for orthophoto, digital elevation model, stereoscopic models, and so on. Like, for instance, Moscow region, there are many people from there. We have like 44,000 square kilometers on a good plane with 25 centimeter resolution. So it just takes just 4 or 5 hours in one day with good flight plan you can do, cover the whole area. Productivity of processing, like orthophoto building productivity, of course, largely depends on some of the parameters. One of them is resolution. Cross overlapping and so on, but for that, for 25 centimeters, we can have up to 9,000 square kilometers per day. It's one day, and as long as this is an automatic system, nobody needs to operate this processing process. We just launch the projects, and every day you can get 9,000 square kilometers. The ground point resolution is easy to calculate, 2.5 centimeters for every kilometer of altitude. So if it is only 1 kilometer altitude, you have 2.5 centimeter ground resolution. 2 kilometers, 5 centimeters. 10 kilometers, 25 centimeters. This way, the system, generally speaking, can get a plane and oblique imagery. That's why it is very user-friendly for all sorts of applications related to building 3D city models, dense DEMs, also monitoring of urban development area with the oblique imagery and so on. In the oblique imagery mode, this system is much more productive than all other so-called penta cameras. Standard cameras for oblique imagery would be cameras with 5 lenses usually, usually short focal length, central lenses usually for 50 millimeter focal length, and oblique ones is 80 millimeters, so you have to fly very low, which is simply impossible for urban areas. We can fly higher at the same altitudes as usual, so there are no restrictions in altitude-wise for urban areas, and because we can fly high, the productivity will be 2-3 times higher. And this is a fully automatic system. The processing is also fully automatic, and it can in fact create 4 or 5 different products, which is automatic triangulation, DSM, digital surface model, and just like everyone, we are doing dense DSM. This is pixel by pixel digital surface model. We're also using semi-global matching. Also, we do regular orthophotos and the so-called true orthophotos, which are based on dense DSM. So true orthophoto is a relatively new product for us. It is interesting, and it can be acquired without any additional costs. When you make color point cloud, which is based on image, by preserving this in orthogonal projection, you can build a true orthophoto. In many cases, when we need true orthophoto, that's how it is done all over the world, and this is a dynamically developing area. Maybe in terms of the quality of image, it is less high quality than regular orthophoto, but in terms of such parameters as price per square kilometer, it's many times less expensive. And in the final analysis, it can deliver the information which most of the users require. Accuracy 25 centimeters without any ground control points. For that, we can use all sorts of processing, GPS, DPP, or DGPS. If we use GCPs, then it will largely depend on the accuracy of the GCPs themselves. What products? Actually, I mentioned them, the vertical oblique imagery, which can be with proper orientation too, because all vertical and oblique images are triangulated, jointly triangulated. That's why their rectification is done with high precision. and it is fully in line with the general triangulation precision. General triangulation precision is usually 0.3, 0.4 pixels, which is at the moment is a standard. According to many global instructions, we can build stereo pairs for stereo vectorization. Many softwares support the stereo pairs. The stereo pairs are not a standard vertical projection stereo pair. This is more like quasi-panoramic projection, but we can supply all the necessary formulas, DNL, and we are compatible with most of the software developers in the world. The company Rakurs and their PhotoMod is the most compatible software that we have. They are the best in that respect, so that's why we recommend using PhotoMod to do this processing for true orthophoto, which is done automatically again. We can do automatic stitching and radiometric correction. We also build dense DSM, which is dense point cloud, and we don't have 3D city modeling software. We have integrated with the French company Acute 3D. Those of you who use AGI Soft can be use Ubisoft also. We have integrated it with AGI Soft 2 and any other one. We have a number of packages to build the 3D models. Once we have integrated with AQ 3D, because at the time they were the most advanced, providing the best quality of models and high productivity, which is important in our case. And in principle, their model is included into the general technological scheme, and the person who did it, he didn't even feel that they need to do it manually. It's not manual, it's automatic, in fact, with just some additional element of data transfer. And the use of oblique images, we use Oblique Vision software. It's a well-known Israeli software which is broadly used in Israel. Like 100% of all Israeli companies use this, and also in the world it is well presented in the world. We also recommend using it, but we have integrated it with a Belgian software called OrbitGIS, and with Blom as well. We had a joint one with Blom. So one can use different things here. And the last product jointly done with the Israeli company Video Inform. It is a video profiler in an automatic object detection software, very powerful software, and I will show you how it works. It's not the only one in the world.
But apparently it's executed very well. It's based on deep learning, and it allows you to recognize automatically various objects on the ground. It can be mounted on any aircraft, starting from light and ending with the heaviest ones. The one on the left is the most lightweight we used in Russia. Then there is another small jet, Leargy. So any aircraft that has a standard hatch to hook up any standard analog camera can do it. I mean, you can mount it in a short period of time, 5 to 10 minutes. We don't require specialized mounting. We use the coupling device with 4 bolts and 4 screws, and that's it. This picture shows how it flies, but I decided not to use any video clips. This shows you how the image shift compensation system works. Motion compensation. I have all of this on my computer. You interested? I'll show you later. So this is the primary idea of our patent, not using gyrostabilizing systems, but rather going with motion compensation technology. It allows you to replace a heavyweight gyro stabilizer that compensates airplane vibration and opt for motion compensation technology, which includes a 10-gram mirror that is mounted on 3 gyroscopic motors. And it's not the camera that we're compensating, it's the light entering the camera. We are diverting it to the right place, the place where it should be, based on estimated motion. This idea is not new. It was described in a well-known book on aerial photography by Mr. Schlopak in 1959. And this is how it was executed in modern days. And it works very well. Why such high productivity? First of all, you fly higher. Since your focal distance is 300 millimeter and your competitor has 100 millimeter, which is close to the truth, you can fly 3 times as high. And the 2 alpha angle is an effective angle used for creating orthophoto images. It's described in our guidelines, Russian and international guidelines. If you use the same effective field of view, you will obtain larger coverage. It's as simple as that. Plus, we have 110-degree field of view, whereas others offer 50 or 60. So we can afford to fly with a large, and that is 55-60% of side overlap. This side overlap allows building a solid triangulation block, meaning you have overlapped on the very third image, so you have very strong triangulation block. You don't need an IMU, and this does not come as standard package. So there is a number of advantages that allows you down the line to generate high accuracy, photogrammetric and surveying alike. This is how this swath from a standard camera looks. So there's large format cameras. You know what they are. This is what we generate, A3. This is comparison of productivities from various cameras. This is A3 Edge, then A3 Edge in infrared mode, infrared in other words, infrared imaging, more or less. And other cameras, they have their own intrinsic differences, of course, but the major difference is up here. I mean, starting from 10 centimeter accuracy. This is where the difference becomes most potent, 2 to 5 times. This comparison is based on distances between surveys. First, in one case you can capture kilometers, and the other mode is where you measure distance between routes. 2 alpha angle, that is. It's standard for certain resolutions on the ground. That allows you to make adequate comparisons, and this is what I recommend because it is free of influence from other parameters. This is a spreadsheet of productivity. 10 centimeter resolution, 25 will give you 6.665. This table shows links between standard side overlap and the A2 alpha. It's the same. Standard side overlap is 20, 30 or 40%. We used to say that because all cameras were the same. They were standardized. In the West, it's 24 by 24 centimeters. In Soviet Union, it was 18 by 18 centimeter with a standard set of focal distances. So when we do an urban settlement, side overlap was 40%. Village area was 20%. People haven't really given much thought to other parameters. Today, things differ. All cameras have different sizes, different CCDs, different data acquisition methods. Some use several lenses, line sensors. In other words, the design of cameras varies. Focal distances vary. So planning a flight mission no longer makes sense, meaning if you commission 40% side overlap, it will mean different things for different cameras. There are different geometries of orthophoto that you will collect from different sensors. So this is a totally wrong approach to plan the mission this way. In some countries, this has become the regulation or the guideline to enter the building angle, inclination, or to use the effective field of view. So this table provides connection to understanding what 2 alpha means and how it relates to side overlap. Now a few words about software. The software covers everything: flight planning, navigation, camera management during flight, flight viewer. That's a pleasant software. It allows you on the fly and right after the flight to verify the quality of your flight. I mean, have you captured everything? Did you do a good job? I mean, if you had any you could do it on the plane. It works fast. And if you still have flight time left, you can turn around and finish the section that failed for some reason, like high visibility, overcast skies. So this is a fairly new development that is 2 years old. Fast Mosaic is based on Flight Viewer. In civil applications, it's not very relevant. I mean, for disaster management, it's more relevant. It is quick to collect mosaic right from the takeoff. It's not orthophoto, no triangulation used, but it will give you a certain accuracy. Data viewer is one of the key systems allowing you to launch projects, analyze them, generate reports, do external orientation, measure points. Then control and processing center includes light speed, that is responsible for aerial triangulation, DSM creation, and orthophoto production. These are three main processes that you can do. You can do several parallel projects running at the same time, or have clusters of projects, and you can monitor it while sitting in an office in Tel Aviv, while a project is being done in Los Angeles, in LA. I know that it's not allowed in Moscow. That's why I didn't mention it. So you can control it via internet. And the same is true for a camera. When we provide support to our users, first thing we do it through is the internet. So you can connect it online, check for any errors, connect it to the ground station, and help our users remotely, help them set things right if they're not able to do it themselves. This is one of our main companions. That is photo mode by Rakurs for stereo compatibility. They really did a very good job, better than anybody else. They do support it at a single image level or quasi-panoramic image, one strip, adjacent strips, and we always recommend using it in marriage with our system. 3D city modeling is where we rely on acute 3D a lot. As for oblique imagery, this is where we use Oblique Vision from IDAN computers, and automatic object recognition is where we use Visual Profiler. I'm going to show you a couple of images that we obtained. The system can consist not necessarily of 64 cores. It could be 260 cores if it's a large corporation requiring a lot of productivity. We have them too, but a standard setup, standard configuration for civilian applications is 20 to 20 cores for mobile system, and this is a fixed configuration, 64 up to 64 cores. Prices are very low, and you can buy it at 10 to 12,000 for 10 to 12,000 dollars. If it's Delta, $45,000, and if it's something simpler, then it's 25. Prices are down substantially. Productivity rates are much better, and you of course can continue to improve. There are users that use both systems. There is a French company working a lot in Africa. So in the HQ they use this system, and when it comes to field work, then they use less complicated system. Now, as for light speed processing, restriction is 250 images per block. This constraint has been removed. Now we're talking about unlimited number of images, and you can process in one block an unlimited number of images, no limits. 1 million images, fine. You have 1 billion images, still fine. They will still be adjusted. For 10 centimeters, that's 1,000 kilometers per day. For GSD 39,000 kilometers. Block area restriction used to be relevant too, but not anymore. You can use territory of Russia in one single block. Accuracy certification. We successfully passed certification in Stuttgart. There's a report that you can look up online, we talk about accuracy with ground control points, 0.3 to 0.5 pixel in plan and 0.8 in height. This is part of our deal, part of the contract, what we commit to ensure, to commit to deliver. And a couple of images where this can be applied. This is Jerusalem, GSD 5 centimeters, altitude 2 kilometers. You can see all the stones. I don't think this is something to write home about. I mean, it's quite common these days. This is St. Petersburg, Isaac's Cathedral, captured last year for orthophoto plans and for oblique imaging as well. This is St. Petersburg, the same part of the same project. This is where we used our system in the forestry sector in Russia, infrared mode, again infrared. This is an interesting project, altitude 12.5 kilometers, GSD 30 centimeters. This entire area was covered in 3 strips in 27 minutes and processed in just one single night. This is dense DSM. It looks like a true ortho photo, so pixel by pixel DSM. It's not a picture, it's a color point cloud. GSD 5 centimeters. Every 5 centimeters there is a dot, there is a point, a dot. So 400 dots per square meter, and each dot, each point has a color. This is a true ortho that is developing around the world, becoming highly popular. Another true ortho, oh no, this is dense DSM in Atlanta, 10 centimeter GSD, an immense area. 150 square kilometer with 10 centimeter. We did it in 81 hours. But this is 2 years old. Now it's getting done much faster because we parallelized this processes. Another example of dense DSM. One more example. This is oblique images. Use oblique images. Oblivision enables creating projects that include orthophoto layers from JS layers and oblique imaging. By indicating a point, the software shows you how it looks.
Here you can see all the oblique images that look at this point. You can do mono measurement, not stereo, but mono measurement of all images that you have here, and see what you have. It is done to monitor large construction sites, large factories, and to inventorize the residential housing in the cities. This is a 3D model, a small castle in France. We have many models like this already, made by our users and clients. This is another 3D model from the United States. This is one of the largest iron ore mining company from Australia, Newman Mine. All these models can be found on my computer, where you can see how it works in real time. This is the last product that we have, the automatic object detection. Here we were detecting cars in Tel Aviv for a project to detect parking areas in large cities. And here we were detecting automatically cars. And you can see how well the program works. Even in the darkest areas of a city, it can detect all these objects. Here we were also detecting empty parking spaces. In many cases, we need to know where there are parking lots and where they're vacant. Here we were detecting animals in Africa. Last year we're flying over Africa and we're cooperating with local organizations who are into animal detection. We were detecting elephants, antelopes. I didn't show you antelopes. Anyway, any kind of animals, because we can fly quite high and get a high resolution, 4 to 5 centimeter, which it is very good to monitor animals. Here you can see our global operation, basically where we are present in the world. And that would be the end of my presentation. If you have questions, I'll gladly answer them. Huh? My question about true ortho. You don't do true ortho? Yeah, we have true ortho photo. Of course, we do this. Moreover, no, true ortho as a cloud or as DSM plus classical raster methods, not just ortho, but true ortho. No, we've never had true ortho. We've never had regular visual true ortho. We had true ortho photo based on cloud point. My question is about regular orthophoto. For regular orthophoto, the digital terrain model is acquired from where? Digital terrain model is acquired by our system. We do not acquire a digital elevation model. We get DSM that needs to be filtered in DTM into digital terrain model. Then we do filtering using standard methods like TerraSolid could be used for that. So it's not part of your package, no. We supply just TerraSolid. Sergey Kudenko, Prime Group Moscow. Can you tell me whether you had experience of working with your camera with big altitudes by building DTM? I'm not sure about DTM building, but for instance, orthophoto plans, one of the first users would be our Belgian company Aerodata, who were using it in Central Europe for mountainous areas, and they did orthophotos there based on our DTM with filtration, land-based filtration. We don't need to filter it too much because it's an open area. We have received no complaints. The accuracy is the same everywhere based on this. In fact, good afternoon. Do you wish to mount a laser scanner on your sensor for DEM? We had such an idea to combine this, because we had a rotating company, we wanted to have an add-on, but so far it's just an idea. Victor Hodorov is saying that I'm over my time limit.
I should cut my speech.
Can I still ask one last question? Center of Digital Technologies about detection. You used what characteristics for detection? RGB, I'm talking about the volume of data, and what is the real time for object detection? Yes, like you showed the parking areas. Yeah, I have a separate presentation about this. And during the break, if you're interested, we can have a sit down. I will show you how the image was analyzed. It works for any kind of information, can be colored information or even thermal information, infrared data. As far as time is concerned, if you're interested, I can show it to you. And the question to continue, what methodological instruments did you use for this? It was depilling, yes, mostly based on neural networks. So can we now? Of course, during the break I can answer all the additional questions.